Now that we have a general idea about circular motion and centripetal force, we're going to dig a little deeper into the material and see if we can't come up with some tools to help us be quantitative about circular motion, right? We want to be able to quantify motion in numerical terms, right? That's what we're doing when we use math. We want exact answers, not just general answers. So let's take a closer look at circular motion and see what we can come up with. We're going to use the same example as the previous podcast, okay? I've changed the speed slightly up in the upper left-hand corner. You can see my 5 meters per second, so I'm using metric units now, so those will play nice with our formulas. We have a free body diagram of the object at this point again, okay? If you remember, we had the force normal, right? Force of weight and the force of friction, which was actually the force acting as a centripetal force. Now, we've already concluded that this object is accelerating, right? The car is accelerating. Even though the speed is constant, the car is accelerating because it's changing direction. The problem is, if you try to calculate that acceleration, right, using your acceleration formula from the first semester, final minus initial, you run into a problem. You get 0 as your numerator. Right? Because if the speed's not changing, right, the speedometer says the same number the whole time, then the final minus the initial is going to be 20 minus 20, right, or 5 minus 5. It's going to be 0. And yet we know that the object is accelerating, and the acceleration can't be 0. Okay, so what this means is that when we're moving in a circle, we're actually going to have to use a different expression for acceleration. Okay, it's actually related to the one that you see on the screen, but using a little math and physics wizardry, you can derive, that's the word we use in physics, you can derive a new equation. I'm just going to present it to you. I'm not going to expect you to follow or understand how we got it. You just need to be able to use it. So what you need to understand is that we're moving in a circle, okay? When we're moving in a circle, we can't use our usual acceleration formula. We have to use a new one. And that new one is going to be like this. It'll be A for acceleration, subscript C for centripetal, and it's going to be v squared over r, okay, the square of the velocity divided by the radius. So let's use it right away. Let's try over here. We can calculate the centripetal acceleration of this car. Okay, it's moving 5 meters per second squared divided by 150 meters, okay, and this is going to be 25 meters squared per second squared. I'm going to show you that the units work out here. Okay, 25 goes into 156 times, so that's going to be 1/6, right? And then notice how the units cancel. We still get meters per second squared, okay? Or if you want to put this in decimal terms, we still get meters per second squared, which we know are the units of acceleration. Okay, so you're going to use this new formula, right? Anytime you get to acceleration, okay, in circular motion, you're going to use the boxed one instead of the top one. All right. We can continue to apply this acceleration equation to another equation that we know, which is F equals ma. Okay. So what's going to happen is that F equals ma is also going to change slightly when you're using it in circular motion. You're going to replace this a with v squared over r, like this. Okay. So we could ask another question here. We could ask, what is the force of friction required to keep this car moving in the circle that's being shown? Okay. So let me do that for you. Let me show you how we do that. We still want to retain this approach of separating our horizontal motion from our vertical motion. So notice in this example that the centripetal motion, the circular motion, is happening in the x direction. And if you look in the x direction, right on our free body diagram up here, okay, you see that the only force in the x direction is the force of friction. Okay, and so this side gets replaced by the single force in the x direction. And then on the right side, all we have is a v squared over r. We're going to replace the a with v squared over r because in the x direction, the horizontal direction is the direction in which centripetal motion is happening. And then all you have to do here really is plug and chug. I'm going to be a little tight on space here, so I'm going to shift things over a little. But basically, you just put your 2,000 kilograms in. Okay, that's a realistic weight. It's about 4,000 pounds, right? 4,200 pounds for a car. And let's see here, 5 squared over 150. All right, so I can do that math. And I won't show you the units, but these units will work out to newtons if your velocity is in meters per second and your mass is in kilograms. Okay, so you can pause here and do this on the calculator. Okay, this comes out to 333 newtons. All right, so the force of friction to keep this car moving in a circle is 333 newtons. And when I actually used a calculator, I realized up here a little earlier I made a mistake. This actually works out to 0.1667, so that's 0.17, so 0.18. Okay, so you've just used Newton's second law in circular motion to calculate the force of friction. You familiarized yourself with centripetal acceleration. We want to do one more thing. We want to get a feel for how does the centripetal acceleration change when the car speeds up, slows down, makes a bigger circle, makes a smaller circle. So for that, I'm going to switch to the next screen. Okay, we're going to consider the following example. We're going to have this car speed up. It's going to triple its speed, but it's also going to make a bigger circle. So we want to know whether the end result of that is going to be that the acceleration is bigger or smaller than it was originally. Now, in this case, you could just plug all the numbers in and then divide, and you could do it that way, but that's more work than you really need. Plus, it's also kind of short-circuiting your conceptual understanding of the situation. So first of all, you should look at the following. You should be clear about, does speeding up or slowing down, how does the velocity change affect acceleration? Okay, if you come over here and look at the expression, you can see that if I make this numerator bigger, right, then I'm going to get a bigger number. In other words, speeding up means more acceleration. Whereas if I make the denominator bigger, okay, that's going to be a smaller number, a smaller acceleration. In other words, doubling the speed is going to increase the acceleration, but doubling the radius is going to decrease the acceleration. So they kind of have an offsetting effect. So when you look at this example, right, you can see that the speed triples, okay, so that's going to be increasing acceleration, working one way, but the radius doubling is going to make it be less. So overall, how's it going to work out? Is it going to work out to be more or less than the original? All right, so let's try it. Let me show you how we're going to do it. We're not going to use the numbers. We're going to do what's called proportional reasoning. So I'm going to write some things out, and we'll come back. Okay, you see on the screen the acceleration from the previous page. All right, we worked it out to be 0.17 meters per second squared. Now watch how I'm going to do this to get my answer. Okay, for the new acceleration, I'm going to write it out this way. I'm going to write a new, okay, and I know that the new speed, okay, is 3 times the original speed. So I'm going to write that like this, 3v, and that's going to get squared, right? And then the new radius is twice as much, right? Like that. And then I'm going to multiply everything out. Okay, notice that this is going to work out to 9v squared over 2r. And then I can pull this 9/2 out in front, okay, like this. All right. And I can see, remember this right here represents the original acceleration, which was 0.17. And you can see that even though making the radius bigger makes acceleration less, making the velocity bigger makes acceleration more, and that effect has a greater effect, right? Changing velocity has a greater effect because it gets squared. So actually, this is 9/2 is 4.5 times as much, right? 4.5 times 1.17. In other words, when I make these changes, I'm going to get an acceleration that's 4.5 times as much. But notice that I didn't have to plug in all the numbers, like the velocity is 5 and the radius is 150. I can do it just by working with these factors here, right? We call these factors. And this kind of approach is called proportional reasoning, and it saves you time and it saves you calculation. So you'll be expected to do this on upcoming quiz and tests.